Hello, my name is Pat Long. I'm a student in Old Dominion's Mechanical Engineering Technology program. I would like to present my senior design project for Mechanical Engineering Technology 435. The title of my project is Compact Cascade Refrigeration System Utilizing Hydrocarbon Refrigerants. Many of today's traditional refrigerants pose a threat to the ozone layer and also contribute to global warming. Some natural refrigerants are being looked at as possible replacements for these. All the natural refrigerants have their benefits and their inherent risk. Ammonia poses no threat to the ozone and has a very low global warming potential. The downside is its toxicity. Carbon dioxide is used as the baseline for rating the ozone depletion potential of refrigerants. It has an ozone depletion potential of 0. Carbon dioxide, though, has a high working pressure and requires special components to handle these pressures. Hydrocarbons have no ozone depletion potential and a very low global warming potential. But the downside is their flammability. Is the main concern behind their use. As mentioned before, the prime reason to use hydrocarbon refrigerants are the fact that they have low ozone depletion potential and low global warming potential. Unfortunately, the public needs to be educated. The public has many misconceptions about hydrocarbon refrigerants. One is the size of the charge that is used in appliances that are currently out there, such as the ice chest and the refrigerators. ASHRAE currently has limitations on that to limit their explosive capability. And in the primary use would be in appliances. Typically 4 ounces is the size of the charge that they're currently used. In large commercial plants, the plants are located away from areas where they can pose a threat to the public. In the cascade refrigeration system, the heat is removed from the refrigerated space and rejected to the atmosphere in 2 stages. This is more efficient than a single stage compression system. Heat is rejected from the R170 to the R290 via an interstate heat exchanger. This is a pressure versus enthalpy diagram of both refrigeration cycles overlaid upon each other. From point 4, the point 1 represents the evaporating of the R170. From point 1, the point 2 represents the compression of the R170. Point 2 to 3 represents the condensing of the R170 within the interstate heat exchanger. And from point 3 to point 4 represents the expansion of the R170 within the capillary tube. From point 8 to point 5 represents the evaporating of the R290 within the interstate heat exchanger. And from point 5 to point 6 represents the compression of the R290. And point 6 to point 7 represents the condensing of the R290. And from point 7 to point 8 represents the expansion of the R290 within the thermal expansion valve. In this area is the area where there has to be a minimum of a 10-degree overlap that causes a sufficient amount of heat exchange within the interstate heat exchanger. Calculations predict that the airspace within the refrigerated space will achieve minus 60 degrees Fahrenheit. This is caused by the R170 evaporating at minus 70 degrees Fahrenheit. Calculations also predict that once the R170 is compressed, it will condense at 0 degrees Fahrenheit within the interstate heat exchanger. Likewise, the R290 will evaporate at minus 10 degrees Fahrenheit within the interstate heat exchanger. After compression, the R290 will condense at 95 degrees Fahrenheit. The purpose of constructing an operating cascade system was to demonstrate the two hydrocarbon refrigeration cycles. A primary goal during the construction of the system was to utilize off-the-shelf components, such as compressors, thermal expansion valves, and condensing units. The ideal system was a system that was outlined in the paper. It would have used the exact components proposed and calculated for, and would have produced the results as calculated. The real system was a system that was put together as the cost rose above budget, and components were substituted to stay within budget. The system that was put together demonstrated the hydrocarbon refrigeration cycle and showed its viability. This is a photograph of the system as constructed, the real system. Component number 1 is the low side evaporator. Component number 2 is the low side filter dryer. Component number 3 is the capillary expansion tube. Component number 4 is a low side compressor. Component number 5 is the expansion tank to hold the charge of the R170 during off cycles. Component number 6 is the interstate heat exchangers. Component number 7 is the high side receiver that holds the refrigerant. Component number 8, which is behind the bracket, is the filter dryer for the high side. Component number 9 is a sight glass to view the refrigerant flow. Component number 10 is the expansion valve. Component number 11 is the high side compressor. And component number 12 are the high side condensers. As the high side was ran, adjustments were made to the thermal expansion valve to try to achieve the correct amount of temperature within the interstate heat exchangers. This is the first try. This is the second adjustment on the high side expansion valve. This is the third adjustment made to the high side expansion valve. This is the lowest temperature that was able to be achieved. Frosting can be seen on the interstate heat exchangers. Unfortunately, the R290 thermal expansion valve could not be adjusted to achieve the minus 10 degrees Fahrenheit in the interstate heat exchanger without being able to properly condense the R170. The low side operating system could not be ran for more than a few seconds. The possible cause of this was an obstruction in the thermal expansion valve. A replacing of the thermal expansion valve would most likely have alleviated this problem. If the system was ran again, it would have been closer to the results calculated in the paper. I thank you for your time in viewing my senior design project.